Some galaxies are weird, aren't they? In this video, you're going to learn why some galaxies have such bizarre shapes. We'll look at the forces that cause them to form this way, along with the math behind it. If you're a space enthusiast like me, this channel is for you. Let's get started. Look at this photograph. Really look at it. This is a galaxy. A city of stars, hundreds of billions of them. But something is wrong here. This galaxy has a hole in its middle, a perfect ring of stars with nothing at the center. It looks like someone took a cosmic cookie cutter and punched through the heart of space itself. Now look at this one, a galaxy with a tail, not just any tail. A tail that stretches for hundreds of thousands of light years across the void. Stars ripped away from their home and flung into the darkness like water droplets from a spinning wheel. And this, two galaxies locked together in what can only be described as a train wreck. Twisted metal on a cosmic highway, stars scattered everywhere, arms torn and stretched. The beautiful spiral structure destroyed. For over a century, astronomers have looked at these images with growing confusion. These are not the neat, orderly galaxies we see in textbooks. These are monsters. These are victims. These are the aftermath of something violent. The question that has haunted scientists is simple. What could do this? What force in the universe is powerful enough to take something as massive as a galaxy and twist it into these bizarre, impossible shapes? Tonight, we are going to find the answer. And that answer begins right here, in our own cosmic backyard. This is the Milky Way, our home. Right now, at this very moment, you are standing on a planet orbiting a star inside this galaxy. Look up at the night sky on a clear night away from city lights, and you will see a river of stars flowing across the darkness. That river is your home galaxy, seen from the inside. The Milky Way is what we call a spiral galaxy. Imagine looking down at a hurricane from space. You see the spiral arms. You see the structure. That is what our galaxy looks like from above. A flat disk with graceful arms curving outward from a bright center. It is beautiful. It is orderly. It is peaceful. Inside this galaxy live 200 billion stars, each one a sun. Many of them with their own planets. It is a city in space, and like any city, it has structure. The stars do not just float randomly. They move in orbits around the center. They follow the traffic patterns set by gravity. Everything flows. Everything has its place. Our sun lives in the suburbs of this galactic city, about halfway out from the center. We orbit the galactic core once every 230 million years. A cosmic year. Dinosaurs walked the Earth 1 galactic year ago. Think about that. The last time our sun was in this exact spot in the galaxy, T-Rex was hunting beneath alien stars. But we are not alone in space. Look beyond our galaxy and you will find neighbors. The closest large galaxy to us is called Andromeda. It looks like a smudge of light to the naked eye. Through a telescope, it reveals itself as another spiral, another city of stars. This one even bigger than ours. Perhaps 1 trillion stars call Andromeda home. There are other neighbors too, small galaxies, dwarf galaxies we call them, the Large Magellanic Cloud, the Small Magellanic Cloud. From the southern hemisphere of Earth, you can see them without a telescope. They look like pieces of the Milky Way that broke off and drifted away. For billions of years, this has been our neighborhood. Quiet, peaceful, everyone keeping to themselves. Or so we thought. Because in the 1920s, everything changed. An astronomer looked at these galaxies more carefully, and he discovered something terrifying. His name was Edwin Hubble. And before you ask, yes, the Space Telescope is named after him. But Hubble was not always an astronomer. He was a lawyer first. Then he was a boxer. He fought professionally, won his matches. But the stars called to him. So he left the courtroom and the boxing ring and pointed telescopes at the sky. In 1929, Hubble made a discovery that changed everything we thought we knew about the universe. He looked at distant galaxies and measured their light. That light was shifted toward the red end of the spectrum. This red shift meant something crucial. Those galaxies were moving away from us. The universe itself was expanding. But here is where the story takes a dark turn. Almost every galaxy Hubble looked at was moving away. Almost every galaxy, but not all of them. When Hubble and his colleagues looked at Andromeda, they found something different, something that should have been impossible. The light from Andromeda was shifted toward the blue end of the spectrum. Blue shift means one thing: approach. Andromeda was not moving away from us. It was coming toward us. Scientists measured the speed, 250,000 miles per hour, fast enough to cross the distance from Earth to the Moon in less than 1 hour, and it was aimed directly at us, at the Milky Way, at our home. The next question was obvious. When will it hit us? Astronomers calculated the distance. Andromeda is 2.5 million light-years away. At its current speed, it will take approximately 4 billion years to reach us. Let that sink in for a moment. In 4 billion years, the Milky Way and Andromeda galaxies will not be separate anymore. They will collide. Two cities of stars, each containing hundreds of billions of suns, will smash together in the most violent event our corner of the universe has ever witnessed. Computer simulations show us what this will look like. First, Andromeda grows larger in our night sky. Slowly at first. Over millions of years, it gets bigger and bigger. Eventually it dominates the sky. A massive spiral stretching from horizon to horizon. Then the two galaxies touch. Stars are flung in every direction. Tidal tails, hundreds of thousands of light-years long, stream into space. The cores spiral around each other like dancers in a deadly waltz. Gas clouds crash together. Millions of new stars burst into existence. The night sky becomes brilliant with their light. And finally, after billions of years of violence, the two galaxies merge. They become one, a new galaxy. Scientists have already given it a name. Milkomeda, the child of the Milky Way and Andromeda. But it will look nothing like its parents. The beautiful spiral arms will be gone. In their place will be a smooth, featureless blob, an elliptical galaxy, a graveyard of old stars. Now, before you start panicking, let me assure you of something. We will not be here to see this. Humanity will be long gone. In fact, our sun will be dying right around the same time this collision happens. So this is not our problem. This is a problem for whatever comes after us, if anything does. But here is the thing. If this collision is going to happen to us, then maybe it has happened to other galaxies already. Maybe that is why we see all those bizarre shapes in the universe. Maybe every strange galaxy we see is just a collision in progress, a cosmic car crash frozen in time by the vastness of space. And that raises the most important question of all. If we want to understand what is going to happen to US, we need to understand what happened to them. We need to investigate these galactic crime scenes and figure out what kind of violence created these shapes. For most of human history, we did not even know galaxies existed. When you look up at the night sky, everything looks like it is part of one thing, one cosmic painting. The ancient Greeks saw the Milky Way and thought it was literally milk spilled across the heavens by a goddess. It was not until the 1600s that telescopes revealed the truth. That band of light across the sky was not milk. It was stars. Countless stars too faint to see individually, all blending together into a river of light. But the real revelation came in the 1920s. Edwin Hubble again. He looked at fuzzy patches of light that astronomers had been seeing for centuries. Patches they called nebulae. Clouds of gas, they thought. Hubble used the most powerful telescope in the world at the time and looked closer. Those fuzzy patches were not clouds. They were galaxies, entire other galaxies. Island universes separate from our own. Suddenly, the universe got a lot bigger. We were not alone. There were millions of these galaxies out there, maybe billions. And as telescopes got better and better, astronomers could see them in more and more detail. That is when they started noticing the bizarre shapes. Most galaxies looked normal enough, spirals like ours, or smooth elliptical blobs. But some looked wrong. Some looked like they had been in an accident. At first, astronomers thought these might be mistakes. Maybe the telescope was not focused properly. Maybe there was a flaw in the photographic plate. But the shapes kept showing up, over and over, in different telescopes, in different observations. These shapes were real. What astronomers were looking at were not mistakes. They were evidence of cosmic violence. Each bizarre galaxy was a crime scene. And like detectives studying a crime scene, astronomers had to learn how to read the evidence. They had to figure out what kind of event could create each strange shape. Over the decades, patterns began to emerge. Galaxies with rings seemed to have one thing in common. Galaxies with tails had a different story. Merging galaxies showed yet another pattern. Each type of bizarre shape was like a fingerprint. It revealed the type of collision that created it. Tonight, we are going to tour the most spectacular collision sites in the universe. We are going to look at the evidence. We are going to piece together what happened, and by the end, you will be able to look at any bizarre galaxy and read its story. You will see the violence that created it, and you will understand the forces that shape our universe. Our investigation begins with perhaps the most beautiful type of collision, the kind that creates rings of fire in the darkness of space. Chapter 1. Ring Galaxies, the bullseye effect. This is Hoag's object, named after the astronomer who discovered it in 1950. When Arthur Hoag first saw this galaxy through his telescope, he thought something was wrong with his equipment, because this galaxy looked impossible. It is a perfect ring, a circle of stars floating in space with absolutely nothing in the middle. The center is completely empty, just darkness, just void. Around that void, stars form a nearly perfect circle, like someone drew it with a cosmic compass. It looks artificial. It looks like something that could not possibly exist naturally. Hoag studied this object for years. He wrote about it. He showed it to other astronomers. Everyone agreed it was bizarre. Everyone agreed it looked impossible. But there it was, real, undeniable, a cosmic mystery. And Hoag's object was not alone. As telescopes surveyed more of the sky, more ring galaxies appeared. The most famous is called the Cartwheel Galaxy, and this one gives us the first clue about what is going on. The Cartwheel Galaxy is 500 million light-years away. That means the light we see from it left that galaxy 500 million years ago. When that light began its journey to Earth, the first fish were just beginning to crawl onto land. Think about that. We are not seeing this galaxy as it is now. We are seeing it as it was in Earth's ancient past. And what we see is extraordinary. The galaxy has two rings, an inner ring and an outer ring. The outer ring is bright blue. Brilliant young stars are being born there. The inner region is more yellow, older stars. And connecting the center to the outer ring are spokes, like the spokes of a wheel. This is why it is called the cartwheel. For decades, this galaxy puzzled scientists. Then someone had a breakthrough. They realized that ring galaxies might not be a permanent feature. They might be temporary. They might be the result of something passing through the galaxy. Here is how it works. Imagine you have a pond. The surface is perfectly calm. Now drop a stone into the center. What happens? A ripple spreads outward, a circular wave moving away from the impact point. Now imagine that instead of water, the pond is made of stars. And instead of a stone, a small galaxy punches through the center. The small galaxy passes through. Its gravity does not push stars outward directly. Remember, stars are very far apart. The small galaxy's stars do not hit the larger galaxy's stars. What happens is more subtle. The gravity of the passing galaxy pulls on all the stars. It creates a wave, a ripple in the fabric of the galaxy itself. This ripple pushes stars outward. As the ripple expands, it compresses gas clouds. Compressed gas collapses. Collapsed gas forms new stars, thousands of them, millions of them, all forming at once in a ring that expands outward like the ripple in a pond. This is what we are seeing in the Cartwheel Galaxy. That brilliant blue outer ring, those are baby stars, stars that were just born because a small galaxy punched through the center and created a cosmic ripple. And here is the amazing part. If you look carefully at the Cartwheel Galaxy, you can find the culprit. Off to the side, there are two small galaxies. One of them passed through the cartwheel 200 million years ago. It left this ring as evidence of its crime, and it is still there, still nearby, unable to escape the cartwheel's gravity. Eventually it will fall back in and do it all over again. Let me be clear about something important. When a small galaxy passes through a large galaxy, the stars do not actually hit each other. Space between stars is enormous. If our sun were the size of a grain of sand, the nearest star would be 4 miles away. So, when two galaxies pass through each other, the stars mostly slip past one another like two swarms of bees passing through each other. But even though stars do not collide, gravity still affects everything. Every star in the small galaxy pulls on every star in the large galaxy, and vice versa. It is this gravitational interaction that does the damage. It is gravity that creates the ripple, gravity that pushes stars into new orbits, gravity that compresses gas and triggers star formation. This is the secret of cosmic collisions. It is not about things crashing, it is about gravity. Gravity is the sculptor. Gravity is the artist. And gravity creates some of the most beautiful structures in the universe. Ring galaxies are relatively rare. We have found only a few hundred of them in the entire universe, and that rarity tells us something important. Ring galaxies do not stay rings forever. The ring expands. Over hundreds of millions of years, it gets bigger and fainter. Eventually, the ring dissipates. The stars spread out. The galaxy rebuilds itself, returns to something more normal. What we are seeing when we look at a ring galaxy is a moment in time. A frozen snapshot of a cosmic event that takes hundreds of millions of years to unfold. We are like someone looking at a photograph of a water droplet hitting a pond. We see the splash, we see the ripple, but we are seeing just one instant in a process that continues long after the photograph was taken. The universe is full of these moments. Frozen violence, cosmic collisions happening in ultra-slow motion, and ring galaxies are just the beginning. They are the simplest type of collision, the appetizer. Now let me show you what happens when collisions get more complicated. Chapter 2. Tadpole and Streamer Galaxies. The Long Goodbye. This is the Tadpole Galaxy. Its official name is UGC 10214, but nobody calls it that. One look tells you why. This galaxy has a tail, an enormous, impossible, ridiculous tail. The galaxy itself looks relatively normal, a spiral, maybe a bit distorted. But that tail, it stretches for 280,000 light-years into space. To put that in perspective, our entire Milky Way galaxy is only 100,000 light-years across. This tail is almost 3 times wider than our entire galaxy, and the tail is not made of gas. It is not made of dust. It is made of stars. Billions of stars ripped away from their home galaxy and flung into the void. They form a line, a river of stars flowing away from the galaxy like water from a broken dam. What could do this? What force could rip stars away from a galaxy and stretch them into a line hundreds of thousands of light-years long? The answer lies in something you experience every day. Tides. You know about tides from the ocean. Twice a day the water rises, twice a day it falls. This is caused by the moon. The moon's gravity pulls on the Earth. But here is the key thing. The moon pulls harder on the side of Earth closest to it, and it pulls weaker on the side farthest away. This difference in gravitational pull creates a stretch. The oceans bulge out on both sides. One bulge toward the moon, one bulge away. As Earth rotates, these bulges stay in place, but the land rotates underneath. This is what creates tides. Now scale this up. Instead of the moon pulling on Earth, imagine a small galaxy passing close to a large galaxy. The gravity of the small galaxy pulls on the large galaxy. But just like with tides, it pulls harder on the near side and weaker on the far side. This creates a stretch. Stars on the side closest to the passing galaxy get pulled toward it. Stars on the far side get left behind. The galaxy is stretched like taffy, like pulling apart a piece of warm candy. The galaxy elongates, stretches, and eventually stars on the ends break free completely. They stream away into space, forming long tails. This is what happened to the tadpole galaxy. A smaller galaxy passed close by. Too close. Its gravity reached out and grabbed the tadpole, stretched it, pulled stars away. Those stars now form the tail we see. They are orphans, ripped from their home, doomed to drift through space for billions of years. And here is what makes this even more dramatic. This is happening right now. Well, it was happening 280 million years ago, which is when the light we see left that galaxy. But from our perspective, frozen in this moment, we can see the violence in progress. We can see stars actively being pulled away. The tadpole galaxy is not alone. The universe is full of galaxies with tails, some with one tail, some with two. Each tale tells the story of a close encounter, a gravitational mugging, a cosmic theft. Look at the mice galaxies, two galaxies that look like mice running away from each other. Each one has a long tail streaming behind it. But these mice are not running away. They are falling toward each other. They already had one close pass. That pass created the tails. Now gravity is pulling them back together. Eventually they will collide again, and again, until finally they merge into one. Or look at the antennae galaxies. Two galaxies with tails so long they look like insect antennae reaching into space. These antennae are made of stars. Millions and millions of stars pulled away from their home galaxies during the initial collision. Those stars will never return. They are lost, cast into the darkness between galaxies. This is the thing about tidal tails. They are permanent. Once stars are pulled away from a galaxy, they do not just fall back. They have been given enough energy to escape. They will drift through space essentially forever. Orphan stars with no galaxy to call home. Imagine what it would be like to have a planet orbiting one of those orphan stars. You look up at your night sky, and instead of seeing one galaxy, you see two or three. The remnants of the collision scattered across the heavens. Multiple galaxies, all visible at once, chaos in the sky. But here is what is really mind-blowing about tidal tails. Remember, we are seeing these tails in the light that left these galaxies millions or billions of years ago. By the time that light reaches us, crosses the vast gulf of space, and enters our telescopes, those galaxies have continued evolving. The tails have changed, grown longer, or dissipated, or been absorbed back into the galaxy. What we see is a fossil, a frozen moment, like finding dinosaur bones and trying to imagine what the living animal looked like. We see the bones of cosmic collisions, the remains, the evidence, and from that evidence we piece together what happened. The tadpole galaxy, the mice, the antennae. These are all different stages of the same basic process. Close approach, tidal stretching, tail formation. Some are early in the process, some are late. By studying many different examples at different stages, we can piece together the entire story. We can watch the movie of galaxy collisions frame by frame. And the movie is about to get even more violent. Because tidal tails are just the beginning. They form during close approaches, during the first pass. But many galaxies do not just pass once. They pass multiple times. They lock together in a gravitational embrace. And when that happens, when galaxies actually collide head-on, the real destruction begins. Let me show you the most important collision site in the universe, the one that has taught us more about galaxy collisions than any other, the one we call the antennae. Chapter 3, The Antennae, Our Rosetta Stone. 45 million light-years from Earth, two galaxies are dying and being reborn. At the same time, these are the antennae galaxies, NGC 4038 and NGC 4039. Those are their catalogue numbers, but everyone calls them the antennae because of those two long tidal tails streaming away into space like insect feelers reaching into the void. Why are these galaxies so important? Why do scientists study them more than any other collision? The answer is simple. They are close. In cosmic terms, 45 million light-years is practically next door. This means our telescopes can see incredible detail. We can zoom in, we can see individual star clusters, we can watch the violence up close. The antennae are our Rosetta Stone for understanding galaxy collisions. Just like the Rosetta Stone helped us decode Egyptian hieroglyphics, the antennae galaxies help us decode the language of cosmic collisions. Everything we learn here applies to collisions everywhere in the universe. So let us walk through the history of these two galaxies. Let us reconstruct their story from the evidence. 1 billion years ago, these were two separate spiral galaxies, each minding its own business, each making stars at a leisurely pace, each with beautiful spiral arms and an organized disk structure. They were normal, peaceful, boring, but they were also close together, part of a small group of galaxies, and in groups, gravity is always at work, always pulling, always tugging. Over millions of years, these two galaxies were pulled toward each other, slowly at first, then faster. 900 million years ago, they had their first close approach. They passed within a few tens of thousands of light-years of each other. In galactic terms, this is close, dangerously close. The gravitational pull between them was enormous. Stars from each galaxy began to be pulled toward the other. The first tidal tails formed, long streams of stars ripped away and flung into space. But they did not merge yet, not on the first pass. They swept past each other like two cars narrowly avoiding a collision on a highway. But their fate was already sealed. Gravity had locked them together. They could not escape each other anymore. They were doomed to fall back together. 600 million years ago, the second approach happened. This time, they actually touched. The outer parts of the galaxies began to interpenetrate. Stars from one galaxy passed through the disk of the other galaxy. And this is when things got violent. Remember, stars do not hit each other, but gas clouds do. Both galaxies had enormous clouds of hydrogen gas, raw material for making stars. When the galaxies collided, these gas clouds smashed into each other at speeds of millions of miles per hour. When gas clouds collide at those speeds, they create shock waves, like sonic booms. These shock waves compress the gas, squeeze it, and compressed gas collapses under its own gravity. When enough gas collapses in one place, it ignites. A new star is born. Now imagine this happening not in one place, but in thousands of places, simultaneously across both galaxies. Millions of new stars bursting into existence all at once. This is called a starburst, and it is one of the most violent events in the universe. Look at the Hubble Space Telescope images of the antennae. In the region where the two galaxies overlap, you see brilliant blue clusters. Each cluster contains thousands of newly formed stars, stars so young they are still hot, stars so massive they burn blue-white. These are the children of the collision, born in violence. But starburst stars come with a dark side. These massive blue stars burn fast. They use up their fuel in just a few million years. Compare that to our sun, which will burn for 10 billion years. These massive stars are like flashbulbs, bright for an instant, then dead. And when massive stars die, they die violently. They explode as supernovas. Each supernova releases as much energy in a few weeks as our sun will release in its entire lifetime. Now imagine thousands of these explosions happening in a small region of space over just a few million years. The blasts destroy any remaining gas. They blow it out of the galaxy entirely. And when the gas is gone, no new stars can form. The starburst ends as quickly as it began. Today, in the antennae, we see this process in full swing. The cores of the two galaxies are deep in merger. They are spiraling around each other, getting closer with each orbit. In the overlap region, we see both the bright blue new stars and the first supernovas starting to go off. Scientists estimate that in about 400 million years, the merger will be complete. The two galaxy cores will have combined into one. The tidal tails will slowly dissipate as the stars spread out, and what will remain is a single elliptical galaxy. Round, featureless, filled with old stars. No more star formation, no more beautiful spiral arms, just a graveyard. But here is what makes the antennae even more important. We are not just seeing one moment in time. Because of the antennae's size and detail, we can see multiple stages of the collision happening simultaneously in different parts of the galaxies. In one region, we see the initial tidal stretching, stars just beginning to be pulled away. In another region, we see gas clouds colliding and forming stars. In another, we see older starburst regions where the first supernovas are already going off. In yet another, we see the cores merging. It is like watching a movie where all the frames are visible at once. We can see the beginning, middle and approaching end, all in one image. This is why the antennae are so valuable. They are a complete tutorial on galaxy collisions, compressed into one observable system. Now, let me tell you a human story. These galaxies were first discovered in 1785 by William Herschel. Herschel was a musician who became an astronomer. He built his own telescopes, big ones, and he spent night after night sweeping the sky, cataloguing everything he could see. When Herschel looked at the antennae, he saw two fuzzy patches. He drew them in his notebook. He gave them numbers. He had no idea what they were. He thought they were nebulae, clouds of glowing gas somewhere inside our own galaxy. He did not know they were galaxies. He did not know what a galaxy even was. The concept had not been invented yet. Herschel certainly did not know these two objects were colliding. To him, they were just two more fuzzy blobs in a sky full of fuzzy blobs. Now, 240 years later, we can look at the same objects Herschel saw, but we see them with knowledge. We see them with Hubble Space Telescope. We see them with radio telescopes and X-ray telescopes. We can measure the motion of the stars. We can trace the tidal tails. We can see the newborn stars glowing blue. We can detect X-rays from the gas-heated to millions of degrees. We can reconstruct the entire history of these galaxies going back 1 billion years and project their future forward 500 million years. We can watch them die and be reborn. All because they are close enough for us to study in detail. This is the power of astronomy. This is the power of human curiosity. A musician in 1785 points a homemade telescope at the sky and sees fuzzy blobs. 2 centuries later, we see a cosmic drama spanning billions of years. We see violence and creation intertwined. We see the universe reshaping itself. The antennae taught us the language of galaxy collisions. Now let us use that language to read other collision sites, because the universe has many stories to tell, and some of them are even more chaotic than the antennae. Chapter 4. Train wrecks and pile-ups. 300 million light-years from Earth, 5 galaxies are locked in a gravitational nightmare. This is Stephan's quintet, and it is the most chaotic collision site we have ever found. Look at this image. Look at it. Try to make sense of what you're seeing. 5 galaxies all in the same small region of space. Galaxies stretched and distorted. Tidal tails everywhere. Stars scattered across the field. Long streamers of gas. Shock waves visible even in optical light. This is not a collision. This is a demolition derby. But wait, it gets more complicated. Those 5 galaxies, only 4 of them are actually interacting. The 5th one is in the foreground. It just looks like it is part of the group. It is actually much closer to us. 7 times closer. It is photobombing one of the most violent scenes in the universe. The 4 galaxies that are interacting are moving through each other at 2 million miles per hour. That is fast, even by cosmic standards. They are not just passing by. They are ploughing through each other, gas clouds colliding, stars being flung in every direction, gravitational chaos. And the amazing thing? We can see the shock waves. When galaxies collide at such high speeds, the gas does not just heat up. It creates shock fronts, like the shock wave from an explosion. These shock fronts are visible in X-ray and infrared light as bright glowing regions. The gas is heated to millions of degrees, hot enough to glow in X-rays. Stefan's quintet has been colliding for hundreds of millions of years, and it is not done. These galaxies are gravitationally bound to each other. They cannot escape. They will continue to interact, continue to collide, again and again. Until eventually, millions of years from now, they merge into a single giant elliptical galaxy. But Stefan's quintet is not unique. In 1982, an astronomer named Paul Hickson published a catalogue of compact galaxy groups. He found 100 of these groups, collections of 4 or 5 or more galaxies, all packed together in a small volume of space. Every single one of these groups is a future collision site. Some are in early stages, galaxies just starting to distort each other. Some are in mid-collision, like Stefan's quintet, and some are in late stages, nearly merged. Just a few hints of the violence that created them. These compact groups are laboratories for studying galaxy evolution, because in these groups, collisions are not rare events. They are common. They are inevitable. When you pack multiple galaxies into a small space, gravity will eventually pull them together. There is no escape. Look at Hickson Compact Group 44. 4 galaxies in a tight embrace. Tidal tails connecting them like strings. Stars pulled from one galaxy being absorbed by another. Gas stripped away and forming a common envelope around all 4 galaxies. This is not 4 separate objects anymore. This is one system. One chaotic, violent, beautiful system in the process of becoming one galaxy. Or look at Hickson Compact Group 90. This group is in late-stage merger. The individual galaxies are barely recognizable anymore. They have merged into a blob, a train wreck so complete that you cannot tell where one galaxy ends and another begins. This is the future of all compact groups. This is the end point. Now, here is the question. What determines how messy a collision gets? Why do some collisions produce clean rings, others produce tidal tails, and others turn into complete train wrecks like Stefan's quintet? The answer comes down to several factors. First, speed. Fast collisions are more violent. The galaxies do not have time to gently interact. They slam into each other. Gas clouds collide at higher speeds. Shock waves are stronger. Stars get thrown farther. Second, angle. A head-on collision is different from a glancing blow. Head-on collisions maximize the interaction. The galaxies pass directly through each other. A glancing blow might just create tidal tails. The galaxies might sweep past each other and escape. Third, size. When 2 galaxies of similar size collide, they can lock together. Neither one is strong enough to escape, but when a small galaxy hits a large galaxy, the result is different. The small galaxy might punch through, create a ring, or get ripped apart and absorbed. Fourth, number. Collisions between two galaxies are complex, but collisions involving 3 or 4 or 5 galaxies, that is chaos, pure chaos. Every galaxy pulls on every other galaxy. The gravitational interactions become unpredictable. The result is a train wreck. Think of it like car crashes. A fender bender at low speed leaves both cars mostly intact. A high-speed head-on collision totals both vehicles. A multi-car pile-up on a highway creates a scene of complete destruction where you cannot tell which parts came from which car. Galaxy collisions work the same way. And here is the beautiful thing. Every collision is unique. No two are exactly the same. Each one depends on the exact speeds, angles, sizes and orientations of the galaxies involved. Each collision creates its own unique shape, its own unique fingerprint. This is why the universe is full of such bizarre galaxies. Every collision creates something new, something unexpected, something that has never existed before and will never exist again in quite the same way. We have catalogued thousands of colliding galaxies, and each one is different. Each one is special. Each one tells its own story. The universe is not just violent, it is creative, it is an artist, and gravity is its brush. Collisions are how it paints. But we have been focused on what these collisions look like from the outside. What about the inside? What happens to the stars when galaxies collide? What happens to the planets? What happens to any civilizations that might exist on those planets? That is where our investigation goes next. Chapter 5. What happens to the stars? Here is the question everyone wants answered. When two galaxies collide, when hundreds of billions of stars pass through each other, how many stars actually hit each other? The answer will surprise you. 0, or close enough to 0 that it makes no difference. Let me explain why. Our Sun is 93 million miles from Earth. That is one astronomical unit. The nearest star to our Sun is called Proxima Centauri. It is 4 light-years away. A light-year is 6 trillion miles. So Proxima Centauri is about 25 trillion miles away. Now think about that ratio. The nearest star is about 270,000 times farther away than the distance from the Earth to the Sun. The space between stars is enormous, unimaginably empty. Here is an analogy that might help. Imagine shrinking the Sun down to the size of a grain of sand. A tiny grain of sand sitting in the palm of your hand. On this scale, how far away would the nearest star be? Another grain of sand 4 miles away. 4 miles of completely empty space between 2 grains of sand. Now imagine 2 swarms of these sand grains, each swarm spread out over hundreds of miles, and you throw these swarms at each other. What is the chance that any 2 grains of sand will actually collide? Essentially 0. This is what happens when galaxies collide. The stars are so far apart that they simply pass between each other, like 2 clouds of gnats flying through each other. The individual gnats rarely touch, but just because stars do not hit each other does not mean nothing happens to them. Far from it. Every star feels the gravity of every other star, and that gravity changes everything. Imagine you are a star in a spiral galaxy. you have a nice circular orbit around the galactic center. You have been following this orbit for billions of years. Everything is predictable, orderly, safe. Then another galaxy arrives. Suddenly, there are hundreds of billions of new sources of gravity pulling on you, stars from the other galaxy, each one exerting its gravitational influence. All these gravitational tugs add up. They change your orbit. Maybe you get pulled toward the center of your galaxy. Your nice circular orbit becomes elongated. You fall inward, speed up, swing around the center, then fly back outward. You are on a new orbit, an orbit you never intended. Or maybe you get pulled away from the center. The gravity of the passing galaxy grabs you, accelerates you, gives you enough energy to escape your home galaxy entirely. You become an orphan, an intergalactic star, doomed to drift through the void between galaxies forever. This is what happens to stars during collisions. They get thrown onto new orbits, random orbits, chaotic orbits. The beautiful organized structure of the spiral galaxy is destroyed, replaced by chaos. Computer simulations show us exactly what this looks like. Start with two spiral galaxies, each one orderly, each star moving in a neat circular orbit around the center. Now let them collide. Watch what happens. At first, nothing seems to change much. The galaxies pass through each other. Stars slip between stars. But then gravity takes effect. Stars begin to deviate from their orbits. Some get pulled inward, some get thrown outward. Tidal tails form as stars stream away into space. As the galaxies make multiple passes, the chaos increases. More and more stars are thrown onto random orbits. The spiral arms disappear. The organized disk structure breaks down. What is left is a blob. Stars moving in every direction. No pattern, no structure, just chaos. This is how spiral galaxies become elliptical galaxies. Collisions destroy the order, replace it with randomness. The stars are still there. They did not go anywhere. But their orbits changed. And the shape of a galaxy is determined by the orbits of its stars. Now, let me tell you about the orphan stars, the ones that get thrown out of their home galaxies during collisions. Scientists estimate that in some collisions, up to half of the stars from both galaxies can be ejected into intergalactic space. These orphan stars drift through the darkness between galaxies. They are not bound to any galaxy. They do not orbit any galactic center. They are truly alone. And here is the thing. If these stars have planets, those planets go with them. The star's gravity holds onto its planets just fine. So these orphan star systems drift through intergalactic space with their planetary families intact. Imagine living on a planet orbiting an orphan star. You look up at your night sky, and instead of seeing the band of the Milky Way stretching across the heavens, you see nothing. No home galaxy. Just a few galaxies in the distance. Tiny smudges of light, millions of light years away. Your sky would be almost empty. Just a handful of stars visible. The other orphan stars that were ejected with you. It would be the loneliest place in the universe. Billions of light years of empty space in every direction. No home to return to, no galactic center to orbit. Just eternal drift through the cosmic void. Scientists have actually found some of these orphan stars. They glow faintly in the space between galaxies in galaxy clusters. When we look at large clusters of galaxies, we see a faint glow between the galaxies. This glow comes from billions of orphan stars, refugees from past collisions, all drifting through the intergalactic medium. But here is what is remarkable. Even though stars get thrown onto new orbits, even though some become orphans, the planetary systems survive. The planets stay in orbit around their star. Life, if it exists on those planets, continues. Why? Because the star's gravity holds onto its planets much more tightly than the galaxy's gravity holds onto the star. The distance from a star to its planets is tiny compared to the distance between stars. The gravitational bond is much stronger. So during a galaxy collision, from the perspective of someone on a planet, here is what they would see. First, another galaxy appears in their night sky. It grows larger over millions of years. Eventually, it dominates the sky, a massive spiral stretching from horizon to horizon. Then the collision begins. New stars appear in the sky as the two galaxies overlap. Brilliant blue starburst regions light up. The night sky becomes brighter than it has ever been. More stars visible than ever before. Their own star continues orbiting normally. Their planet continues its orbit around their star. Nothing changes locally. But the view of the universe changes dramatically. After the collision, after the galaxies merge, the night sky looks completely different. If they are lucky enough to remain in the merged galaxy, they see a smooth distribution of stars, no more spiral arms, just a uniform glow. If they are unlucky and their star was ejected, they see almost nothing. Just empty space in every direction. This is what awaits our own solar system when the Milky Way and Andromeda collide in 4 billion years. Our Sun will continue to exist. Earth, if it still exists, will continue orbiting the Sun, but we will be on a new orbit around the new galactic center. Or we might be ejected entirely. Either way, the night sky our descendants see will be utterly alien compared to the sky we see today. Stars survive galaxy collisions, but they are forever changed. Their homes destroyed, their futures uncertain. They become refugees in a universe that is constantly reshaping itself. And now let me tell you what happens to the gas, because that is where things get truly violent. Chapter 6. The gas crisis, where new stars are born. Stars might pass between each other without colliding, but gas is a different story entirely, and gas is where the real violence happens. Galaxies are not just made of stars. Between the stars, filling the space, are enormous clouds of gas, mostly hydrogen, the raw material for making stars. These gas clouds are spread throughout the galaxy. They take up much more space than the stars do. They are like fog filling a forest. When two galaxies collide, these gas clouds do not pass between each other. They crash, head-on, at millions of miles per hour. Imagine two cars hitting each other at highway speed. The metal crumples. The force of impact is enormous. Energy is released. Now scale that up to galaxy size. Gas clouds containing the mass of millions of suns smashing into each other. The energy released is beyond comprehension. When gas clouds collide, they create shock waves, like a sonic boom, but on a cosmic scale. These shock waves ripple through the gas, they compress it, squeeze it, and compressed gas does something remarkable. It collapses. Here is how it works. Gas clouds normally have internal pressure. The particles bouncing around create an outward push that resists gravity. But when a shock wave compresses the gas, it overwhelms that pressure. Suddenly, gravity wins. The gas cloud begins to collapse inward. As it collapses, it breaks into smaller pieces. Each piece continues collapsing, getting denser, getting hotter. Eventually, at the center of these collapsing clouds, the temperature and pressure become high enough for nuclear fusion to ignite. A star is born. Normally, star formation happens slowly. A galaxy might make a few new stars per year. But in a collision, star formation goes into overdrive. We call it a starburst. Thousands of stars born per year, maybe tens of thousands. An explosion of stellar birth. Look at Hubble images of colliding galaxies. In the regions where the gas clouds have collided, you see brilliant blue clusters. Each cluster is a nursery, a place where thousands of stars have just been born. And these are not ordinary stars. These are massive stars, the biggest stars that can exist. 10 times, 50 times, even 100 times the mass of our Sun. These massive stars burn blue. Blue means hot. Hot means energetic. They pump out enormous amounts of light. A single one of these massive blue stars can outshine 10,000 suns. And there are thousands of them in each cluster. Tens of thousands in each colliding galaxy. The starburst region becomes one of the brightest objects in the universe. It can outshine the entire rest of the galaxy. All that light, all that energy, coming from one small region where gas clouds collided. But massive stars have a problem. They burn too hot. They use up their fuel too fast. While our Sun will burn for 10 billion years, these massive stars will die in just a few million years. They are like candles that burn at both ends. Brilliant for a moment, then gone. And when massive stars die, they do not go quietly. They explode. Supernovas. Each supernova releases more energy in a few weeks than our Sun will release in its entire lifetime. The explosion is so bright it can briefly outshine an entire galaxy. Now imagine thousands of these supernovas going off in a small region of space over just a few million years. The region becomes a war zone. Shock waves from one supernova trigger shock waves from others. The blast waves crisscross the region. They heat the gas to millions of degrees. The gas glows in X-rays. And here is the dark consequence. These supernova blast waves destroy the remaining gas. They blow it out of the galaxy entirely. The gas that did not collapse to form stars gets swept away by the violence, shot out into intergalactic space at thousands of miles per second. When the gas is gone, star formation stops abruptly. The starburst ends as quickly as it began. What remains are the stars that formed, the massive blue stars. But they are dying, exploding as supernovas. Within 10 million years, they are all gone. All that remains are the longer-lived, smaller stars, and the corpses of the massive stars, neutron stars and black holes. The starburst leaves a scar on the galaxy. a region stripped of gas, unable to make new stars, aging rapidly. Scientists call these regions post-starburst. They are bright for a brief cosmic moment, then fade into darkness. Look at the antennae galaxies again. In the overlap region, you can see the starburst happening right now. Brilliant blue clusters, new stars being born by the millions. But look carefully at the edges of that region. You can see older clusters, clusters where the massive stars have already died. These regions are fading, turning yellow, aging before our eyes. This is the life cycle of a starburst. Birth in violence, brilliant youth, rapid aging, then death. All compressed into a few tens of millions of years, faster than the blink of an eye in cosmic time. And this process is not just happening in colliding galaxies. Starbursts can happen anywhere gas clouds collide violently. But galaxy collisions are the best way to trigger them, because galaxy collisions bring together enormous amounts of gas in the same place at the same time. Scientists estimate that in some galaxy collisions, more than half of the gas in both galaxies gets turned into stars during the starburst phase. That is an incredible amount of star formation. Billions of years of normal star formation compressed into a few million years. But there is another consequence of starbursts, another type of violence. Because all this star formation, all these supernovas, all this energy being released, it does not just affect the gas, it wakes up something dark at the center of the galaxy, something that has been sleeping for billions of years. The supermassive black hole. Chapter 7. Supermassive black holes, the hidden monsters. At the center of our Milky Way galaxy, lurking in the darkness, is a monster. A black hole with the mass of 4 million suns, compressed into a region smaller than our solar system. We call it Sagittarius A star, and right now it is mostly sleeping. Every large galaxy has one of these monsters at its center, a supermassive black hole. In Andromeda, the black hole has the mass of 100 million suns. In the giant elliptical galaxy M87, the black hole has the mass of 6.5 billion suns. These are the most massive objects in the universe after galaxy clusters themselves. For most of a galaxy's life, these black holes are quiet. They sit at the center, stars orbit around them, but not much falls in. The black hole is like a sleeping dragon, dangerous if awakened, but mostly harmless as long as it sleeps. Galaxy collisions wake the dragon. Here is what happens. When galaxies collide, all that gas gets disturbed. Remember the shock waves? The compression? Well, not all that gas forms stars. Some of it gets funneled inward, toward the center of the galaxy, toward the black hole. Normally, gas in a galaxy orbits in a nice disk. It has angular momentum. This momentum keeps it in orbit, keeps it from falling into the black hole. But during a collision, gravitational interactions rob gas clouds of their angular momentum. The gas loses its support, and it falls inward. As gas spirals into a black hole, it forms what we call an accretion disk, a swirling disk of material orbiting faster and faster as it gets closer to the black hole. The friction between particles in the disk heats it up, and I mean really heats it up. Millions of degrees, hot enough to glow in 'The accretion disk becomes one of the brightest objects in the universe, a supermassive black hole actively feeding can outshine its entire galaxy. We have a name for these feeding black holes. Quasars. Quasars were one of the great mysteries of 20th century astronomy. In the 1960s, astronomers discovered objects that looked like stars in telescopes but had bizarre properties. They were incredibly bright, brighter than entire galaxies, but they appeared as single points of light like stars. How could something so small be so bright? The mystery was solved when scientists realized these were not stars. They were the bright accretion disks around supermassive black holes at the centers of distant galaxies. The galaxies themselves were too faint and too distant to see. All we could see was the brilliant point of light from the feeding black hole. And here is the connection. Almost every quasar we have studied is associated with a colliding or recently merged galaxy. The collision disturbed the gas, funneled it into the black hole, woke the monster, created the quasar. Look at any nearby galaxy with an actively feeding black hole and you will see evidence of a past collision. Tidal tails, shells, ripples, distorted structure. The collision might have happened hundreds of millions of years ago, but the black hole is still feeding on the gas that was disturbed by that collision. Our own galactic black hole, Sagittarius A star, is mostly quiet. But we have found evidence that it was active in the past. About 6 million years ago, it was feeding. We can see the remnants of that feeding, enormous bubbles of gas above and below the galactic plane, blown out by the energy from the feeding black hole. These bubbles are still there, still expanding, evidence of when our black hole last woke up. But the story gets even more dramatic. When two galaxies collide and merge, they each bring their own supermassive black hole. Two black holes. Both sink toward the center of the merged galaxy. Both feeding on disturbed gas. Both putting out enormous amounts of energy. Eventually, these two black holes find each other. They begin to orbit each other. A binary black hole system at the heart of the merged galaxy. They spiral closer and closer together, locked in a gravitational dance that can only end one way. They merge. Two supermassive black holes collide, combine, become one even more massive black hole. And when they merge, they release an enormous burst of gravitational waves, ripples in the fabric of space-time itself that spread outward at the speed of light. We have not directly detected gravitational waves from merging supermassive black holes yet, but we have detected them from smaller black hole mergers. In 2015, the LIGO detector made history by detecting gravitational waves for the first time. These came from two black holes, each about 30 times the mass of the Sun, merging together. Future gravitational wave detectors, like the space-based LISA mission planned for the 2030s, will be sensitive enough to detect supermassive black hole mergers. When we finally detect one, we will be listening to the final moments of a galaxy collision. The last act of a drama that took billions of years to play out. Think about what is happening during a supermassive black hole merger. Two objects, each containing the mass of millions or billions of suns, spiraling together at a significant fraction of the speed of light. The amount of energy released is staggering, more than all the stars in the galaxy put out in a year, all released in a fraction of a second. That energy does not just disappear, it goes into gravitational waves that ripple through space-time. Any civilization within a few million light years would be able to detect these waves. They would feel space-time itself vibrating, stretching and squeezing ever so slightly as the waves pass by. This is the final step in a galaxy merger. First, the galaxies collide. Gas collides, starbursts happen, the black holes wake up and feed. The black holes sink to the center, they orbit each other, they merge. And finally, after billions of years, the galaxy settles down. One galaxy where there were two. One supermassive black hole where there were two. Everything calm again. The dragon goes back to sleep. Until the next collision. Chapter 8. The Shapeshifters. Transformation. Complete. In 1926, Edwin Hubble published a paper that organized galaxies into categories. He created what we now call the Hubble sequence, a classification system for galaxy types. On one end of the sequence are spiral galaxies, like our Milky Way. These have a flat disk, beautiful spiral arms, young stars, gas clouds, active star formation. They are alive, dynamic, changing. On the other end are elliptical galaxies, smooth blobs, no structure, no spiral arms, no gas, just old stars moving in random orbits. They are dead, static, unchanging. In the middle are various intermediate types, galaxies transitioning from one form to another. For decades, astronomers thought these were different species of galaxies, like cats and dogs, born different, living different lives, dying different deaths. They were wrong. We now know that spirals and ellipticals are not different species. They are different life stages. Spirals are young and middle-aged galaxies. Ellipticals are old galaxies. And the transformation from spiral to elliptical happens through collisions. Here is the life cycle. A galaxy is born as a small proto-galaxy in the early universe. It grows by consuming other small proto-galaxies. Eventually it settles into a spiral. Gas flows inward in a disk. Stars form in the disk. Spiral arms develop. The galaxy enters its youth. This phase can last billions of years. The galaxy makes stars slowly, evolves gradually. Then comes the collision. Another spiral galaxy approaches. They begin their gravitational dance. First approach, tidal tails form. The galaxies are distorted but still recognizable as spirals. This is the disturbed spiral phase. The collision has begun but is not complete. Second approach, the galaxies interpenetrate, gas collides, starburst begins, the galaxies become luminous, brilliant blue light from millions of new stars. But the structure is breaking down, spiral arms disrupted. The galaxies look irregular, messy. This is the merging phase, multiple approaches. The cores spiral together, more gas collides, more starbursts, more supernovas. The gas is consumed or blown away. Star formation begins to shut down. The galaxies look like a train wreck. This is the late merger phase. Finally, the cores merge. One galaxy where there were two, but it looks nothing like its parents. The spiral structure is gone, destroyed by the gravitational chaos. Stars orbit in random directions. No pattern, no order. The galaxy is now an elliptical. Old stars, no gas, no new stars being born. This is the retirement phase. The galaxy will look like this for the rest of its existence. Computer simulations show this transformation in incredible detail. You can watch two spiral galaxies collide, watch them distort, watch the starburst, watch them merge, watch the elliptical galaxy emerge from the chaos. The whole process takes 1 to 2 billion years. A long time by human standards. A blink of an eye in cosmic time. And here is the key insight. Most elliptical galaxies we see in the universe are merger remnants. They are the graveyards of past collisions, the corpses of spiral galaxies that collided and died. But here is the beautiful thing. Even though the collision destroyed the spiral structure, we can still find evidence of it. Scars that remain. Clues that tell us this smooth, featureless elliptical was once something more dynamic. Look closely at elliptical galaxies with powerful telescopes. In many of them you can see faint shells, ripples in the star distribution. These are like the ripples in a pond long after the stone was thrown. They are the fading echoes of the collision that created the elliptical. Or look at the distribution of globular clusters. These are dense clusters of old stars that orbit galaxies. In spiral galaxies, globular clusters follow a predictable pattern. But in ellipticals, especially young ellipticals, the globular clusters are in strange positions. Some orbit in one direction, some orbit in the opposite direction. This is evidence of two populations of globular clusters, one from each of the spiral galaxies that merged. Or look at the motion of stars in the center of ellipticals. In some ellipticals, half the stars orbit one direction and half orbit the opposite direction. A counter-rotating core. This is impossible to create in a single galaxy. It can only happen if two galaxies with different rotation merge together. These are the scars of collision. Even billions of years after the merger, even after the galaxy has settled into a smooth elliptical, these scars remain. Silent testimony to the violence that created it. And here is the fate of most galaxies in the universe. Most galaxies live in groups or clusters. In groups, galaxies are close together. Gravity pulls them toward each other. Eventually, they collide and merge. This is inevitable. In rich clusters, where dozens or hundreds of galaxies are packed together, collisions happen even more often. The center of a cluster becomes a battleground. Galaxies colliding, merging, growing. Eventually, the biggest galaxy at the center of a cluster has consumed most of the others. It becomes a giant elliptical, sometimes called a CD galaxy, the king of the cluster, built from the corpses of dozens of smaller galaxies. Our own Milky Way is part of a small group called the local group. We have Andromeda, we have the Milky Way, we have about 50 smaller dwarf galaxies. Eventually, the Milky Way and Andromeda will merge. We will become an elliptical. The smaller dwarfs will either merge with us or escape. In 10 billion years, the local group will be dominated by one giant elliptical, the remnant of everything that is here today. This is the life cycle of galaxies. Birth as spirals, life making stars, collisions in middle age, death as ellipticals. It is a one-way process. Ellipticals do not become spirals again. There is no going back. The transformation is permanent. But here is what is amazing. Right now, at this moment in cosmic history, we live in a universe full of spirals. Beautiful, dynamic, star-forming spirals. The universe is young enough that most galaxies have not collided yet. Most are still in their youth or middle age. But that will change. As the universe ages, more and more collisions will happen. More spirals will become ellipticals. In the far future, trillions of years from now, almost every galaxy will be an elliptical. Dead, unchanging. The universe will be darker, quieter, filled with galactic corpses. We live in a special time, a time when the universe is still violent, still creating, still transforming itself. We are witnessing the universe in its prime. And these bizarre collision galaxies we see are not oddities. They are the universe at work, creating, destroying, reshaping itself. And now let me tell you about our galaxy's past, because the Milky Way has not been sitting peacefully waiting for Andromeda. We have a violent history of our own. Chapter 9. The Milky Way's Violent Past. For decades, astronomers thought the Milky Way was relatively peaceful. Sure, we knew Andromeda was coming, but we thought our galaxy had been mostly undisturbed for billions of years, growing slowly, making stars at a steady rate, minding its own business. We were wrong. In 2018, the European Space Agency released data from a satellite called Gaia. This satellite has been measuring the positions and motions of more than 1 billion stars in our galaxy. 1 billion. That is about 0.5% of all the stars in the Milky Way. When scientists analyzed the Gaia data, they found something shocking. Some stars in our galaxy are moving in strange directions. They are not following the orderly rotation of the galactic disk. They are moving perpendicular to the disk, or even backwards compared to most stars. These stars are invaders. They did not originate in the Milky Way. They came from other galaxies. Galaxies that the Milky Way ATE. Let me explain. When a small dwarf galaxy gets too close to a large galaxy, like the Milky Way, our gravity rips it apart. The stars from the dwarf galaxy get scattered. Some escape, but most get absorbed into the Milky Way. They become part of us. But they retain their original orbits, orbits that are different from the rest of our stars. By studying these strange orbits, astronomers can reconstruct which dwarf galaxies we ate and when we ate them. It is like forensic science. We are reading the evidence left behind by ancient crimes. The Gaia data revealed at least 5 major past collisions, 5 dwarf galaxies that came too close and got destroyed. Scientists have given these dead galaxies names. The Gaia-Enceladus collision, the Kraken collision, the Helmi stream, the Sequoia collision, the Sagittarius dwarf collision. Let me tell you about the biggest one, Gaia-Enceladus. This was a dwarf galaxy, about 1/4 the mass of the Milky Way. 10 billion years ago, it wandered too close. Our gravity grabbed it, pulled it in. It passed through the Milky Way disk. The collision disturbed our galaxy, heated up the disk, threw stars onto new orbits. Then Gaia-Enceladus came back for a second pass, and a third. Each time, more of its stars were stripped away. Each time, more of its structure was destroyed. Finally, after hundreds of millions of years of this torture, Gaia Enceladus was gone, completely ripped apart. Its stars absorbed into the Milky Way, but those stars are still here, still orbiting. The Gaia satellite found them, millions of stars with strange orbits, all moving together, all remnants of Gaia Enceladus, like a ghost haunting our galaxy. And Gaia. Enceladus was not the only victim. The Kraken collision happened even earlier, 11 billion years ago. We ate a galaxy even bigger than Gaia Enceladus. Most of its stars have mixed into our galaxy, but careful analysis can still pick them out. The Sequoia collision, 9 billion years ago. The Helmy Stream, 8 billion years ago. Each one a dwarf galaxy that came too close. Each one destroyed, each one leaving behind a stream of stars as evidence. And then there is the Sagittarius dwarf galaxy. This one is special because it is being eaten right now, this very moment. The Sagittarius dwarf is on the opposite side of the Milky Way from us, about 50,000 light-years away. It is passing through the disk of our galaxy. Our gravity is ripping it apart. Streams of stars are being pulled away from it. Those stars are joining the Milky Way. This has happened before. The Sagittarius dwarf has passed through the Milky Way disk multiple times over the past billion years. Each time it loses more stars. It is slowly being devoured. In another billion years, it will be completely gone. Its stars scattered throughout the Milky Way. Another ghost to haunt our galaxy. Scientists estimate the Sagittarius dwarf originally had about 10 billion stars. Today, it has less than a billion. We have consumed 90% of it. The rest will follow. But wait. There is more. Look at the Magellanic Clouds. If you go to the southern hemisphere and look up on a clear night, you can see two fuzzy patches. The large Magellanic Cloud and the small Magellanic Cloud. They are small galaxies orbiting the Milky Way. Orbiting for now. The Magellanic Clouds are also being pulled apart by our gravity. There is a stream of gas connecting them to the Milky Way. The Magellanic Stream, a ribbon of hydrogen gas stretching 160 degrees across the sky. This is gas being stripped from the Magellanic Clouds by our gravitational pull. In a few billion years, the Magellanic Clouds will either escape our gravity or be pulled in and destroyed. If they are destroyed, their stars will be added to the Milky Way. We will have eaten two more victims. The Milky Way is a cannibal. We have been eating dwarf galaxies for our entire history. We are not a peaceful galaxy. We are a predator. And this cannibalism has consequences. Every time we eat a dwarf galaxy, the collision disturbs our structure, throws stars onto new orbits, triggers bursts of star formation. Our galaxy has been shaped by this violence. In fact, scientists now believe that most of the stars in the halo of our galaxy came from eaten dwarfs. The halo is a spherical region of old stars surrounding the disk. We used to think these stars formed early in the Milky Way's history, but many of them are invaders, stolen from galaxies we consumed. Our galaxy's history is written in the orbits of its stars, And the Gaia satellite is teaching us how to read that history. Every strange orbit, every counter-rotating star, every stream of stars moving together. These are clues, evidence of past violence, proof that our galaxy has been in cosmic battles throughout its history. But all of this is nothing compared to what is coming, because Andromeda is not a dwarf galaxy. Andromeda is our equal, maybe even slightly bigger than us. When Andromeda hits, it will not be a snack. It will be a collision, a true merger, the most violent event in our galaxy's history, and that collision is coming, closer every day. Let me tell you what it will be like. Chapter 10, The Coming Storm, Andromeda. Approaches right now at this very moment. Andromeda is racing toward us at 250,000 miles per hour. Every hour it gets 250,000 miles closer. Every day 6 million miles closer. Every year more than 2 billion miles closer. It does not sound like much when you say it that way. The distances are so vast. But the clock is ticking. In 4 billion years, Andromeda will be here. Let me walk you through what will happen. Not what will happen to the galaxies in abstract scientific terms. What will happen to anyone living in the Milky Way. What they will see in their night sky. Today, Andromeda appears as a faint smudge in our sky. You can barely see it with the naked eye. It looks like a small fuzzy oval. Through a telescope, it reveals itself as a magnificent spiral. But it is 2.5 million light-years away, very distant, easy to ignore. 1 billion years from now, Andromeda will be noticeably closer. Instead of a faint smudge, it will look like a small galaxy. Clearly visible, clearly spiral-shaped, but still far away, still separate. 2 billion years from now, Andromeda will dominate the night sky. It will appear several times larger than the full moon. You will be able to see its spiral arms with the naked eye. You will be able to see dark dust lanes cutting through it. 2 galaxies visible at once. The Milky Way stretching across the sky like always, and Andromeda looming like a massive spiral storm. 3 billion years from now, Andromeda will fill a large part of the sky. It will be huge, spectacular, terrifying. You will see it during the day, visible even when the sun is up. A pale ghost of a galaxy stretched across the heavens. 3.5 billion years from now, Andromeda will stretch from horizon to horizon. Looking up will be like looking up inside a hurricane. Spiral arms surrounding you. The night sky will be brilliant. Both the Milky Way and Andromeda clearly visible. Billions of stars from both galaxies scattered across the darkness. 3.75 billion years from now, first contact. The outer regions of both galaxies begin to touch. Tidal forces start pulling stars from both galaxies. Long streamers of stars begin forming, stretching away into space. The night sky becomes chaos. Stars everywhere, some from the Milky Way, some from Andromeda. Indistinguishable. 3.85 billion years from now, collision. The main bodies of both galaxies pass through each other. Gas clouds from both galaxies smash together at millions of miles per hour. The collision triggers the most massive starburst in the history of either galaxy. Thousands of brilliant blue star clusters burst into existence. Looking up at the night sky, you see blue, brilliant, eye-searing blue from millions of newly formed massive stars. The night sky is brighter than it has been in billions of years, brighter than it will ever be again. Thousands of supergiant stars pumping out enough light to be visible during the day. The night sky also shows chaos. 2 galactic cores visible, both bright, both spiraling around each other like dancers locked in an embrace, tidal tails streaming away in multiple directions, stars scattered everywhere, the organized structures of both galaxies destroyed. 4 billion years from now, the cores are spiraling closer. The starburst continues. Supernovas are starting to go off. The massive blue stars that formed in the starburst are dying, exploding. You would see supernovas in the sky regularly, maybe one every few years, bright enough to cast shadows at night. 4.5 billion years from now, the cores merge. 2 supermassive black holes combine into one. This releases an enormous burst of gravitational waves. If you had sensitive enough instruments, you could detect space-time itself rippling as the waves pass by. 5 billion years from now, the violence is fading. Most of the gas has been consumed or blown away. The starburst is ending. The massive blue stars are almost all dead. What remains are smaller, longer-lived stars. The night sky is still chaotic, stars scattered everywhere, but it is getting dimmer, calmer. 7 billion years from now, the merger is complete. One galaxy where there were 2. Scientists call it Milkomeda. It is an elliptical galaxy. No more spiral arms, no more disk, just a smooth distribution of stars. The night sky shows a gentle glow of stars in all directions. No structure, no Milky Way band, just uniform light. 10 billion years from now, Milkomeda has settled down completely. Most of the stars are old. There is little gas left for making new stars. The galaxy is aging, dying. The night sky is dimmer than it has ever been. Fewer stars visible. Most of them old red stars near the end of their lives. This is our galaxy's fate. This is our future. If humanity, or whatever comes after humanity, is still around in 4 billion years, this is what they will witness. But here is the question everyone asks. What happens to Earth? What happens to our solar system? The good news is that stars do not hit each other. Remember, space between stars is enormous. The chance of another star hitting our Sun is essentially 0. Our solar system will probably survive the collision intact. The Sun will keep shining, the planets will keep orbiting, but our orbit around the galactic center will change dramatically. Computer simulations show several possible outcomes. In about 50% of simulations, our solar system gets flung to the outer regions of the merged galaxy. We end up in the suburbs, far from the center. The night sky will be darker, fewer stars visible. In about 10% of simulations, we get ejected completely, thrown out of the galaxy entirely. We become an orphan solar system, drifting through intergalactic space. The night sky will be almost empty, just a few distant galaxies. no home galaxy to call home. In the remaining 40% of simulations, we stay somewhere in the middle region of the merged galaxy. Our orbit changes, but we remain part of the galaxy. The night sky will be different, but still populated with stars. But here is the thing. None of this matters for Earth specifically, because the Sun is also dying. Right now, our Sun is in its middle age. It has been burning for 4.5 billion years. It will burn for another 5 billion years. But in about 5 billion years, the Sun will run out of hydrogen fuel in its core. When that happens, the Sun will expand. It will become a red giant. The outer layers will swell up. Mercury will be swallowed. Venus will be swallowed. Earth might be swallowed too. Or Earth might survive but be scorched to a lifeless cinder. Either way, Earth is doomed. And this happens at almost the same time as the Andromeda collision. Both events will occur around 4 to 5 billion years from now, the Sun's death and the galaxy's transformation. Both endings, both beginnings. So, if you are worried about the Andromeda collision affecting Earth, do not be. We have bigger problems. The Sun dying is a much more immediate concern. Well, immediate in cosmic terms, we still have billions of years. But the Andromeda collision is important for understanding what happens to galaxies, what happens to other solar systems, what the far future of our region of space will look like. This is not about us specifically. This is about the universe reshaping itself. And we are along for the ride. Now, let me zoom out even further, because the Milky Way and Andromeda collision is not unique. It is not special. It is happening all over the universe, all the time. Let me show you the bigger picture. Chapter 11. The bigger picture. Galaxy evolution. Galaxy collisions are not rare. They are not unusual. They are fundamental to how the universe works. Collisions are how galaxies grow, how they evolve, how they change. Collisions are not accidents. They are the norm. In the early universe, shortly after the Big Bang, galaxies were small. Much smaller than today's galaxies. These proto-galaxies were more like star clusters, a few million or billion stars each, and they were everywhere, packed together much more tightly than galaxies today. When proto-galaxies got close to each other, they merged. Two became one. That one merged with another. Galaxies grew by consuming their neighbors. This process of merging built up the galaxies we see today. Look at the deep field images from the Hubble Space Telescope. These images show galaxies billions of light years away. We are seeing them as they were billions of years ago. When the light left those galaxies and started traveling toward Earth, the universe was young, only a few billion years old. And what do we see in those images? Chaos. Galaxies everywhere, many of them distorted, many of them colliding, many of them irregular and bizarre. The young universe was a battleground, galaxies crashing into each other constantly. Today, the universe is older, calmer. Galaxies are more spread out. Collisions are less frequent, but they still happen. They will always happen, because of gravity. You see, galaxies are not distributed randomly through space. They clump together into groups and clusters. Our Milky Way is in a small group, the local group. about 50 galaxies all bound together by gravity. The nearest large cluster to us is called the Virgo cluster. It contains about 2,000 galaxies, all orbiting around a common center, all gravitationally bound to each other. In groups and clusters, galaxies are close together. Gravity pulls them toward each other. Collisions are inevitable. In rich clusters at the center, collisions happen often. The biggest galaxy at the center grows by eating the others. It becomes a giant, a monster galaxy built from the corpses of hundreds of smaller galaxies, and here is what is driving it all. Dark matter. This is invisible matter that we cannot see directly, but we can detect its gravitational effects. Dark matter makes up about 85% of all matter in the universe. It is the real structure of the cosmos. Dark matter forms a cosmic web. Long filaments of dark matter stretching through space. Galaxies form where the dark matter is densest. Groups and clusters form at the intersections of these filaments, like cities at highway interchanges. And the dark matter's gravity pulls galaxies together, funnels them toward the densest regions, causes them to collide and merge. Dark matter is the invisible hand sculpting the universe, building structure, creating clusters, driving galaxy evolution. In the far future, this process will continue. More collisions, more mergers. Galaxies in groups will merge into single giant ellipticals. Clusters will be dominated by one monster galaxy at the center. The universe will become populated by these massive elliptical galaxies, fewer galaxies, bigger galaxies, older galaxies, but there is a twist. The universe is expanding, and the expansion is accelerating. We do not fully understand why. We call the cause dark energy. This is even more mysterious than dark matter. Dark energy is pushing space itself apart. On large scales, it is pushing galaxy clusters away from each other, faster and faster. Eventually, galaxy clusters will become completely isolated. They will lose contact with other clusters. The space between clusters will expand so much that light from one cluster can no longer reach another. Each cluster will become an island universe, completely cut off from all other clusters. Within each island, galaxies will continue to merge, eventually forming one giant elliptical. But between islands, nothing. No light, no contact, no communication. This is the far future, trillions of years from now. Island universes scattered through an expanding void. Each island a single giant galaxy. All the stars old. No more star formation. The last red dwarf stars flickering out. Black holes evaporating. The universe growing cold and dark. But that future is so far away, it is almost meaningless. Right now, we live in what scientists call the stelliferous era, the era of star formation. The universe is still young, still bright, still making stars, still violent and dynamic. We live at a special time. Not too early, when the universe was all proto-galaxies crashing together. Not too late, when everything will be dead ellipticals. We live in the middle, the prime of the universe, when spiral galaxies still exist, when collisions create beauty, when the universe is still reshaping itself, and these bizarre collision galaxies we have been looking at, they are not oddities. They are the universe at work. Every ring galaxy, every tidal tail, every train wreck, every starburst. These are the universe creating, destroying, transforming. This is the cosmic perspective. Galaxy collisions are not tragic events. They are not disasters. They are the natural life cycle of galaxies. They are how the universe evolves, how structure forms, how galaxies grow and die and are reborn as something new. There is beauty in this violence. Let me show you. Chapter 12. Beauty in Violence. Look at this image, the antennae galaxies. Two galaxies locked in a death spiral, stars ripped from their homes, gas clouds colliding. Supernovas going off, chaos, destruction, violence. And yet, it is beautiful. Those long tidal tails streaming away into space. They look like the tentacles of some cosmic creature. Graceful, elegant, flowing. The brilliant blue starburst regions. They glow like jewels against the darkness. Each one a nursery. Millions of stars being born in fire and chaos. The pink clouds of glowing hydrogen. Energized by the intense radiation from young stars. They trace the outline of the collision, like paint splattered on a cosmic canvas. This is what I mean by beauty in violence. The collision is tearing these galaxies apart, destroying their structure, ending their existence as separate entities. But in doing so, it is creating something spectacular, something that has never existed before. Every collision is unique. Every collision creates its own art. The ring galaxies with their perfect circular symmetry. The tadpole galaxies with their long sweeping tails. The train wrecks with their chaotic jumble of stars and gas. Each one is different. Each one is special. And here is what makes it even more profound. These collisions are not rare events that we get lucky enough to photograph. They are common. The universe is full of them. Thousands of collision systems visible from Earth with current telescopes. Probably millions more too distant or too faint to see yet. The universe is constantly creating these masterpieces, constantly reshaping itself, using gravity as its sculptor, gas and stars as its medium, and time as its canvas. Time, that is the key. These collisions take hundreds of millions of years, billions of years. From our perspective, looking at a single moment, we see a frozen sculpture, like a photograph of a water droplet hitting a pond. We see the splash, the ripple, the beauty of that single instant. But the collision is not frozen. It is ongoing. The galaxies are moving, changing, evolving. In 1 million years, that collision will look different. In 10 million years, very different. In 100 million years, unrecognizable. We are seeing a snapshot. One frame in a movie that lasts billions of years. And every frame is different. Every moment of a collision has its own beauty. Think about what that means. Think about the scale of these events. Two collections of hundreds of billions of stars, each star potentially with its own planets, each planet potentially with its own story. All caught up in a cosmic dance that transforms entire galaxies. And yet, on the scale of individual stars, individual planets, individual lives, if they exist, the collision might be almost unnoticeable. Remember, stars do not hit each other. A civilization on a planet in one of these colliding galaxies would see their night sky slowly change over millions of years. But their star would keep shining. Their planet would keep orbiting. Life would go on. It is only when you zoom out, when you look at the whole galaxy, that you see the violence, the transformation, the art. This is one of the great paradoxes of astronomy. Events that are catastrophic on a galactic scale are gentle on a human scale. And events that are catastrophic on a human scale are invisible on a galactic scale. But there is another kind of beauty here, a deeper beauty. Because these collisions are not just destroying, they are also creating. Remember the starbursts? Millions of new stars born in the collision. Stars that would never have formed if the galaxies had not collided. The collision created them, brought them into existence, and some of those stars will have planets, and some of those planets might develop life. Life that owes its existence to the collision. Life born from violence. Our own sun might be one of those stars. Scientists believe our sun formed about 4.5 billion years ago in a star-forming region. Maybe that star-forming region was triggered by a collision. Maybe our sun, our planet, our existence is the result of some ancient galactic collision that happened long before our solar system existed. We are made of star stuff. Carl Sagan taught us that. The atoms in our bodies were forged in the cores of stars. Stars that lived and died before our sun formed. Stars that might have been born in the collision that triggered our sun's formation. We are literally made from galaxy collisions. The violence that shapes the universe also shaped us. We are not separate from this process. We are part of it. We are products of it. This is why galaxy collisions matter. Not just because they create beautiful images, not just because they are scientifically interesting, but because they are part of the process that created everything we know, including ourselves. When you look at an image of a colliding galaxy, you are looking at creation and destruction happening simultaneously. You are looking at the universe making itself. And you are looking at your own history, your own origin story written large across the cosmos. There is philosophical weight to this. We live in a violent universe, a universe where galaxies crash into each other, where stars explode, where black holes devour everything near them. It is easy to see this violence as meaningless, as random, as tragic. But it is not meaningless. This violence has purpose, not intentional purpose. The universe does not plan these collisions, but they serve a function. They drive evolution. They create complexity. They make possible the existence of stars and planets and life. Without galaxy collisions, the universe would be simpler, less interesting, fewer types of galaxies, less star formation, fewer of the heavy elements that make planets and life possible. The violence is necessary. It is part of the creative process. This is the paradox at the heart of the cosmos. Creation requires destruction. New things can only come into being if old things are torn apart. This is true on every scale, from the molecular level where chemical reactions break and form bonds, to the cosmic level where galaxies collide and merge. The universe is not static, it is not peaceful, it is dynamic, violent, creative. And that creativity is beautiful even when the violence is terrifying. So when you look at images of bizarre galaxies shaped by collisions, try to see both things at once. See the destruction, the tearing apart of structure, the ending of old order, but also see the creation, the birth of new stars, the formation of new structures, the beginning of something new. This is the true beauty of galaxy collisions. They show us the universe as it really is, not a calm, eternal place, but a dynamic system constantly changing, constantly creating itself, constantly finding new forms, new shapes, new possibilities. And we are fortunate to live at a time when we can witness this. When we have telescopes powerful enough to see these collisions in detail. When we have computers fast enough to simulate them. When we have the knowledge to understand what we are seeing. Humans have looked up at the night sky for tens of thousands of years. For most of that time, we thought the stars were fixed, eternal, unchanging. We had no idea of the violence happening out there, the collisions, the transformations, the constant reshaping of the cosmos. Now we know. Now we can see it. And that knowledge, that vision, changes how we understand our place in the universe. We are not standing apart from the cosmos looking in. We are inside it, part of it, made by it. The violence that shapes galaxies also shaped us. The beauty in that violence is our beauty too, and that is something profound to contemplate. Let us return to where we started. Look again at that ring galaxy, that perfect circle of stars with nothing in the middle. Now you know what created it. A cosmic bullseye. One galaxy punching through another. Gravity creating a ripple that compressed gas and formed new stars in a perfect ring. Look at the tadpole galaxy. That impossible tail stretching hundreds of thousands of light years. Now you know it is the result of tidal forces. A small galaxy passing close and ripping stars away like water from a spinning wheel. Look at the train wreck galaxies, the chaotic tangles of multiple galaxies colliding. Now you know each one is a story of gravitational chaos. Multiple galaxies locked together, unable to escape, doomed to merge into one. Every bizarre galaxy tells a story. And now you can read those stories. You understand the language, the grammar of cosmic violence, the vocabulary of gravitational sculpture. This galaxy had a head-on collision. You can tell by the symmetry. This one had a glancing blow. You can tell by the asymmetric tidal tails. This one is mid-merger. You can tell by the disturbed structure and the starburst regions. This one is a recent merger. You can tell by the shells and ripples fading into the smooth elliptical form. Each shape is a fingerprint. Each tells you what happened, when it happened, how violent it was, what the outcome will be. The universe is full of these stories, billions of them, written in light and gravity across the darkness of space. And the story continues. Right now, as you read these words, collisions are happening. Galaxies are approaching each other. Tidal tails are forming. Gas clouds are colliding. Stars are being born in violence. Black holes are waking and feeding. The universe is alive with motion. Nothing is still, everything is changing, galaxies dancing around each other, falling together, merging, being reborn as something new. In 4 billion years, our own galaxy will join this dance. Andromeda will arrive. The Milky Way and Andromeda will merge. Milkomeda will be born. Our beautiful spiral galaxy will become a smooth elliptical. The change will be complete. But that is far in the future. Right now, the Milky Way exists. Andromeda exists. Both as separate beautiful spirals, both making stars, both alive and dynamic. We live in a moment between, after the past collisions that built these galaxies, before the future collision that will transform them. This is a special time. The universe is in its prime. Not too young, not too old, full of spiral galaxies, full of collisions creating bizarre shapes, full of starbursts lighting up the darkness, full of beauty born from violence, and we are here to witness it. With our telescopes and our computers and our curiosity, we can see across billions of light years. We can look back billions of years in time. We can watch the universe create itself. Think about that. We are inside the universe looking at itself. We are the universe become conscious, able to observe its own structure, able to understand its own processes, able to appreciate its own beauty. The collisions that create bizarre galaxies are not happening to some alien universe far away. They are happening to our universe, the universe we live in, the universe we are part of. When galaxies collide, we are watching the creative force that made US continuing to work. The same gravity that pulls galaxies together pulled together the gas cloud that formed our sun. The same star formation triggered by galaxy collisions formed our sun. The same supernova explosions that destroy gas in colliding galaxies created the heavy elements in our bodies. We are connected to all of this. We are not observers standing outside. We are participants, products of the same processes we are studying, children of the cosmic dance. And the dance goes on. It will continue long after we are gone, long after our sun dies, long after the Milky Way and Andromeda merge, long after the universe grows old and cold. As long as there is gravity, there will be motion. As long as there is motion, there will be collisions. As long as there are collisions, the universe will reshape itself. This is the great lesson of bizarre galaxies. The universe is not fixed. It is not finished. It is constantly creating itself, finding new forms, new structures, new possibilities. And we live at a moment when we can see this process, understand it, appreciate it. Look up at the night sky tonight. You are looking at the Milky Way, our home galaxy. Beautiful, peaceful, orderly, but it will not always look like this. In 4 billion years, Andromeda will dominate that sky, and the collision will begin. You will not be there to see it. No human will. But something might see it. Some descendant, some future form of intelligence, some witness to the transformation. And they will look up and see what we can only imagine. 2 galaxies locked in gravitational combat, tidal tails streaming away, starburst regions glowing blue, the night sky brilliant with newborn stars, beauty born from violence, creation born from destruction. The endless dance continues, galaxies colliding, merging, being reborn. shaping the universe, creating the future. And somewhere in that future, perhaps other beings will look at their sky, see their own bizarre galaxies, ask their own questions, and discover the same truths we have discovered: that the universe is violent, that the universe is creative, that violence and creation are two sides of the same process, and that we and they and all conscious beings are products of that process, children of the cosmic dance, witnesses to the universe creating itself. This is why galaxies are shaped so bizarrely, because the universe is alive, dynamic, constantly changing, constantly creating, using gravity and time and the raw material of stars and gas to sculpt new forms, new shapes, new possibilities. The bizarre shapes are not mistakes. They are not accidents. They are arty. The universe is art, created over billions of years, each one unique, each one beautiful, each one telling a story of violence and creation intertwined. And now you know how to read those stories. You understand the forces that create rings and tails and train wrecks. You understand that these shapes are temporary, moments in a process that spans billions of years, snapshots of the universe at work. You understand that collisions are not rare. They are fundamental. They are how the universe evolves, how galaxies grow and change and die and are reborn. They are part of the creative process that made everything, including us. This is the cosmic perspective. This is what bizarre galaxies teach us, not just about galaxies, but about the nature of the universe itself, about creation and destruction, about violence and beauty, about change and transformation, about our place in it all. We are not separate from this process. We are part of it, made by it, shaped by it. And perhaps someday we or our descendants will witness it firsthand as Andromeda arrives and the Milky Way is transformed. Until then, we can look at images from our telescopes, images of colliding galaxies across the universe, each one a window into our own future, each one a reminder of our own past, each one a work of art created by the only artist capable of working on such a scale. The universe itself, creating, always creating, through violence and beauty and time, shaping galaxies, shaping us, shaping everything. This is the answer to our question. Why are some galaxies shaped so bizarrely? Because the universe is alive, and alive things change, and change creates beauty, even violent change, especially violent change.